We will learn a very important lemma, which is known as palm inversion lemma or palm inversion formula, and we will see some application of that. So the theorem states that if phi is a stationary point process and f be a function of the whole point process taking non-negative values. So this means f is a function from the space of point configuration to r plus. So you the input argument it takes is the complete phi and gives a positive number. Okay, so in that case, if v0 is the Voronoi cell of point at 0 under palm, so you condition that there is a point at 0 and then you take the Voronoi cell of that point. So that is known as a typical cell. Then uh, we can say that E f phi is equal to lambda into palm expectation of integration of shifted phi minus x dx over v0. So the mean of the function is equal to density multiplied by integration of function of shifted point process over each location of the typical Voronoi cell. Okay, so v0 is a typical Voronoi cell, and you want to integrate the function such that you shift each point of the cell and then you integrate it. If these two are equal, that is a statement of palm inversion lemma. Okay, and note that f is a function of phi, not a point, but a complete point process, right? So what can be example of f? F can be, for example, uh, there are 2 points in the ball of radius 10 meters, right? Indicator of that. So if phi has 2 points under the ball of radius of 5 meters, then f will be 1, otherwise it will be 0. So something like that. So palm inversion lemma is basically used to connect the mean of function with its integration over the typical Voronoi cell. Okay, and note that the typical Voronoi cell is the cell of the typical point. So the typical Voronoi cell is the cell of the point at the origin, conditioned on the fact that there is a point at the origin for stationary people. Okay, so a typical Voronoi cell is nothing but the Voronoi cell of origin under palm. So I'll take this basically state that expectation of the function is density multiplied by expectation under palm of typical cell. Okay. So how do we prove this? We use Campbell-Mackay theorem to prove this. Let's first take a function h x comma phi is that distance of the closest point in phi is more than or equal to num of x. If that is the case, then it will be 1, otherwise it will be 0. Right? So this is just an indicator which tells that x is the, there is no point in phi which is closer than x. Okay, so if I construct a ball of radius x from origin, there should not be any point of phi in it. Okay, so note that if you apply this function to all points of phi, only one point can say 1. Okay, and that point should be the closest one. So this means that f phi is equal to summation of f phi into hx phi over all points, right? Note that if you am doing it over all points, but hx phi basically tells if the point, there is no point of phi which is closer than xi, right? So there is no point in phi which is closer to origin than xi. It means xi is the closest point from the origin. Okay, and there can be only one point which is the closest one, right? So only one of the xi will be 1, rest will be 0. So this means this will be equal to fy into 1, and so that is why both left hand side and right hand side is equal. Okay, so for now this looks like a redundant operation, that why we are writing this, but this helps us in writing this function in terms of a summation over all points, right? And once we have a summation over all points, I can apply Campbell-Mackay theorem, because this is the complete thing is nothing but a function of xi and phi. So I can apply Campbell-Mackay theorem. So expectation of Fy is equal to expectation of this, and from Campbell-Mackay theorem, this is given as lambda into integration of palm expectation of Fix Hx comma phi x dx. Okay, so I've applied the Campbell-Mackay theorem to get this. Okay, now what I can do is I can substitute x to minus x, and I will get this, that lambda into palm expectation of phi minus x h minus x comma phi minus x dx. Okay, this just means the same thing, that you are integrating over all points and you condition on a point at origin, and then you shift the point process by minus x, and then you make sure that there is no point closer to origin than x in the shifted origin. Okay, so let us focus on this part actually, h minus x phi minus x. Okay, and there is a conditioning that there is a point at the origin in phi, so there would be a point at minus x for phi minus x. Okay, so there is a point at origin for phi, so this means I'm conditioning that there is a point at minus x in phi minus x. Okay, so if there is a point at origin in phi, this means there would be a point at minus x in phi minus x. Okay, the shifted version. So this means it will be 1, this one, if x satisfy any of the following. These four are equivalent. Right, I'll go them one by one so that you can understand this argument. First of all, by definition, this will be 1 if all points of phi minus x are outside the ball of 0 comma norm of x. That is by definition. Okay, I should have said norm of minus x, but norm of minus x is same as norm of x. This means that all points of phi are outside the ball of x comma norm x. Right? How do we show this? So if right, so if this is my origin, x is my origin, then sorry, yeah. So if you look at this figure, this has phi minus x, and there is a point at minus x. Okay, this is basically showing phi minus x. So there is a point at sorry, this shows phi. So there is a point at the origin, and then I shift it so that I make this my new origin. So this will be phi minus x, and if this is phi minus x, then this point will be at minus x. Okay, and what I mean is that all point, if I make this origin, all point of phi minus x is more is away than origin than this point. Okay, so this basically means that if I look at the original phi, all points, there is no point if I construct a ball of at center x with radius norm x, there is no point of phi in that ball. Okay, so this also means that the closest point from x is the point at origin, right? And this also means that if there's a point at the origin in phi, if I construct a typical cell, x should be part of V0, right? So look at this. If I can, this is point x, and I'm looking at this ball, and there's no other point closer to it, right? So a Voronoi cell means x would be in the Voronoi cell of 0 because it is the closest point from x. Right? That is the definition of Voronoi cell. It consists of all location for which it is the closest one than any other point. So any other point is further away than this norm of x. So x is basically lies in the typical cell of V0. Okay, so I can write this same thing instead, that it is equal to palm expectation of E5 minus x into indicator that x belongs to V0 dx. Okay, so this is what this statement says, that this is the integration of this. This basically means because this is x belongs to v0, so basically I am only integrating over all x such that x belongs to v0. So this is precisely the statement of this palm inversion lemma. Let us see a couple of examples where we can use it. The first one I am going to take is where I just take identity function. So fi is equal to 1 for all phi, right? If I put this, so I get expectation of 1, which is 1. And if I put here, so here, because fi is 1 for all phi, fi minus x will also be 1. Okay, so this is just 1. So this will just become palm expectation of indicator x belongs to v0 dx. Okay, so this will be nothing but lambda into size of v0 and their palm, right? Expected value of v0. Okay, so expected value of v0 is equal to 1 upon lambda. So the size of the typical cell, average size of typical cell is 1 by lambda. So this means the average size of the typical cell is 1 by lambda. Another example we will see. So here I will put fi equal to 1 upon norm of v. Okay, and what is v? V is the tagged cell size. Okay, so you take the point process and you find origin belongs to which point, right? That point is known as the tagged cell, and then you take the size of that tagged cell and you do 1 upon v. So that will be fi, right? Remember, so tagged cell is the cell to which origin connects to, right? Origin is the closest, that point is the closest point from the origin. You tag that, you take its size, its 1i cell size, and then you do 1 upon, and that will be fi. So if I put it here, E of 1 upon norm v, this will give me the average inverse of tag cell, expectation of the inverse of the tag cell. And here if I put, this will be lambda E0 integration of 1 upon v, 1 x indicator v0 dx. Okay. So now note that when this is under the palm expectation, so under the palm expectation, tag cell and the typical cell are the same thing, right? Because remember, tag cell is the one which origin connects to. If there is a point at the origin, then of course that point will be the closest point from the origin. So the tag cell will nothing be will be just the typical cell. So if I take the typical cell, I would put it in, right. Now this is not a function of x, so it will come outside, and then this will be indicated that x belongs to v0 dx, as this will be just size of v0. So here would have I have a size 1 upon tagged cell size into the typical cell size, right? And then the palm both are same, so they will cancel and it will be expectation of 1, which is 1. So you just get lambda. So this means that expectation of 1 upon tagged cell size is lambda. So how does this help? So we note that from Jensen equality, expectation of 1 upon x is more than 1 upon expectation of x. So this means expectation of x is more than equal to 1 upon expectation of 1 by x. So this and now I know that expectation of 1 upon norm v is lambda. So this means expectation of norm of v is more than 1 upon expectation of 1 upon norm v, which is 1 upon lambda. So this means the expectation value of the tag cell is more than 1 upon lambda. Okay, and previously we saw the typical cell expected size is 1 upon lambda. So this gave you that the typed cell is bigger than the typical cell. So this means if I take a point at the origin, and we compute its size, that will be typical cell, or you go to any point and compute its one cell size, that will be the typical cell. And the tag cell would be, if I try to find the cell of the uh, base station to which origin lies in, then that will be a bigger cell than the typical cell. This is known as the Ferrer paradox, uh, which we will explain later on in this class. Stoichiometry, we see a very interesting phenomena which is known as Ferrer paradox, which says that that the cell, the Voronoi cell of a random location is bigger than the cell of a typical point, right? So what does it tell? Formally, let us understand this. So suppose there is some point process. So these are Voronoi cells of that point process. Then first, what I do is I'll arbitrarily select one point of the point process. That will be the typical point. And we will ask what is the area of the Voronoi cell of this point, right? So these all points have equal probability to be selected. We take any point and take its area, and then we average it out. That will be the area of the typical point, right? Sorry, that will be the area of the typical cell or the Voronoi cell of a typical point. Second way what we do is we arbitrarily select one location, right? So suppose this is the location we selected. And then we say, what is the Voronoi cell that contains this location? Tell me the size of that Voronoi cell. And this will be tag cell. Suppose this is the origin or any point, then the point, then the cell to which this belongs is known as the tag cell. And here I'm asking the size of the tag cell. Stoichiometry, we have calculated this using stoichiometry. We found that the area of the typical cell is 1 upon lambda, but the area of the tag cell is more than 1 upon lambda, which means the tag cell is more than the typical cell on the average. Okay, so I will state this in a much known example, which will make it clear why this looks like a paradox. So the one-dimensional variant, which is also known as the waiting time paradox, will make this phenomena more clear. So let us understand. Let us take an example where buses are arriving in time. So the arrival time of buses can be modeled as a one-dimensional point process, right? So assume the time arrival of this buses are a one-dimensional Poisson point process. So these points T1, T2, T4, which are the arrival of the ith bus, are uniformly distributed, on a line. Okay. So what I do is I pick one arrival. I pick one arrival of one bus, which is at time T3, suppose, and then we ask, given the arrival of this point, when is the next arrival, right? After what time the next bus will come. So basically we want T4 minus T3. And then you can show that if it's a Poisson point process, the entire arrival time is exponential random variable with P in 1 upon lambda. So suppose lambda is 1 by 5, which means you would expect one bus each 5 minutes. Okay. So this means in 1 hour, you will expect around mean number of 12 buses coming. Right? So the mean time of waiting would be if you get down from one bus, right, at the bus stand, and if you wait, the next bus will come after 5 minutes, right? So given that you step down from the current bus and you at the bus stop and you wait for the next bus will come after 5 minutes. Okay. Now so this is the typical cell size, typical arrival time. Now let us take another case where we are not selecting one arrival, but we are selecting one time. Right? Let's assume at 2 o'clock. I go to the bus stop at 2 o'clock and then wait for the next bus. Right? When will next bus come? So given any time, if I want to find the nearest arrival, that will be the contact distance. And we know that the contact distance is also distributed as is also an exponential random variable with mean 1 upon lambda. So given at 2 o'clock, the next bus will come after approximately at 5 minutes. Okay. Similarly, if I ask when did the last bus came, so the same way you can say that is also an exponential random variable, and the last bus has arrived on the average 5 minutes before. So what is the inter-arrival time here between two buses? That is 10 minutes. So given, so if you just pick a random user, right, or a random time at the bus stop, and then you ask what is the inter-arrival time between two buses at this point of time, that will be 10 minutes. That will be more than the typical arrival time, right? So this means that if if I'm in the bus and I get down at the bus and wait at the bus stop for the next bus, I will expect the waiting time to be 5 minutes. But if I randomly go to the bus stop, right, there my waiting will also be 5 minutes, which means that given my location, given my arrival there, the inter-arrival time has become 10 minutes. Okay, so this generally means that if I look at from a random user perspective, its inter-arrival is generally bigger than the inter-arrival time of journey you would expect. Right. So if I go down there, if I go at the bus stop, I look at the previous bus arrival, right? Then I would see that I would experience a total inter-arrival time of 10 minutes, right? That will give me an idea that perhaps 6 buses are coming per hour, right? So that will be a wrong estimate. Actually, there are 12 buses are coming per hour, but a random user will just go down to the bus stop at a random time will experience a only 12 minutes of 10 minutes of inter-arrival time. So he would guess that there are only 6 buses coming, right? So there is a paradox there that which one is correct, right? Why a random user which is randomly picked is seeing more arrival time than the reality. Okay, the other example can be other variant of a paradox is known as the Q length paradox, right? Here we will make it clear why this paradox is actually coming, right? So suppose that this paradox generally says that a random user in a supermarket will experience bigger queue. In simply means, if you are a shopper at a supermarket, and generally it was told that there is a typical length of 10 persons per queue, you would experience a bigger queue length in the queue in which you are in. Okay, so let us formally state this. Suppose there are n queues, right? And suppose the queues can be either 1, 2, or 3 length and with equal probability. Then if I want to calculate the average length of queue, right, you would see that 1/3 of the queues on the average have length 1, 1/3 of them has length 2, and 1/3 of them will have 3 length. So the average length of a queue, right? I go to each queue, suppose n queues, add their queue length and compute the average. I would see that average length of a queue is 2, right? That is a very typical queue length, right? And then I would ask that let us pick a random person in the supermarket, look at his queue, and then tell me what is the queue length that person will experience, right? So now there is a bias here because suppose in this example, in this figure, you are seeing total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 persons, right? And if you pick any one of the person, right, there is a 1/12 chance that you will pick this person. So this queue, he will say 1. There is a 4/12 chance that you will pick one person out of this queue, and regardless of who you select, they will all say the queue length to be 4. And then if you select any person here, which is the probability of 1, 2, 3, 4, 5, 6, 7/12, they will say there are 7 persons. Okay, so there is a bias there because if you pick a random person, there is a higher chance that you will pick a random person who is in a bigger queue length, right? just because of the nature of it, right? You're picking a random person, so there is a higher, bigger queue has more persons, so there is a higher chance that they will pick a bigger queue. So let us make a crude calculation. These are not exact, but just give you to give. I will try to give an idea. If I pick a random user and ask is the expected queue length, so assuming n is large, you can show that probability of selecting a user in queue with length 1 is 1 by 6. Probability of selecting a user in queue with length 2 is 2 by 6. And probability of selecting a user in the queue with length 3 is 3 by 6. Okay. So average length, a randomly selected user with experience is 1 into 1 by 6 plus 2 into 2 by 6 plus 3 into 3 by 6, which come out to be 2.33. Right. So if you select average person, he would say the queue length of his queue is to 2.33, while a typical while the supermarket claims that the typical queue length is 2. Right. So the way typical, so which one is correct? Both are actually correct. It just depends what is your perspective. In one way, you are just treating each queue as one identity and you are going to it and computing the average. In the second case is more perspective from the user or the occupant of the queue. And then you go to each user and then ask what is the queue length. So there is a bias going on because there is there's a bias toward larger queues because there is a higher chance that you will select larger queues, right? So if I put that back into this waiting time paradox, the same thing happens here. If I select a arrival time, then this is 5 minutes, right? But then here I'm not selecting the bus, I'm selecting a location, and then you can guess that there's a higher chance that you will select a location which falls in a larger arrival time, right? For example, here you will see if I pick one arbitrary location on this line, there's a higher chance that I will pick one location here, and there is a lower chance that you will pick a location, a time arrival at here, right? So because there's a higher chance of selecting a location falling in a larger arrival time, right? Uh, right. So this means that suppose there are buses coming, and one bus come after 3 minutes, second bus come after 10 minutes, and the next bus come after 2 minutes. In this 15-minute interval. Now, if I select a random time, there is a 2 by 10 by 15 chance that I will select the middle arrival, right? Which is larger. And there is a 3 by 15 chance that I select the first arrival, and the 2 by 15 chance I select the last arrival, right? So if you look at from this perspective, you will of course see a larger arrival time because you are putting a bias on the length of the arrival time. Right. If I go back to the original problem which I had, is here I am selecting typical points. So each of point have equal probability. So suppose these are all base station. I go to each base station and ask what is your size and compute the mean. So each of the base station has equal probability to be selected. Here I am selecting a random location. So of course there is a higher chance that you will select a location or a user in the larger Voronoi. Right. So when you compute the bias, compute the average Voronoi cell, then you will have a higher bias of selecting the bigger average cell. So of course, the average cell a typical user will see is bigger. Okay. So in short, what I want to say here is the size of the typical cell or size of the Voronoi cell of typical base station is 1 upon lambda. But the size of a typical cell for size of the association cell for a typical user, right, is bigger than this, right? So if I select one typical user and ask find the base station you are in and tell me what is the area of that base station, that is generally bigger than the area of a typical base station. Okay, and this comes to an interesting phenomena here that so people have empirically calculated the size. It's actually not possible to compute the analytical values of distribution of Voronoi cells, but empirically they have found, and people have showed that a typical Voronoi cell follows this distribution, right? So, and a typical tagged cell follows this distribution. So average value of the typical cell is 1 upon lambda, and average value of a tagged cell is 1.28 upon lambda. Okay, and because the size is bigger, the number of users will also be more, right? So number of users given an area, or suppose the users are PPP, then given an area, the number of users is Poisson, right? And then you compute the expectation with respect to distribution of the area, and then you can say that expected number of users in a typical cell, right, in a typical base station. So if I select one base station and ask how many users you have, that is lambda u by lambda, right? So if there are 200 users per kilometer square and 20 base stations per kilometer square, on the average you will expect 10 users per base station. Here it says that if you select one user and look at its base station and then ask how many users are there in this base station, then there would be of course one, because you are conditioning that there is one user, and then there will be 1.28 lambda u by lambda times users, right? So it means if I take the previous example, 200 users per kilometer square and 20 base station per kilometer square, this means there are 13.8 users in a in the tag base station, right? So normally you would expect 10 users per base station, but just because you have picked one random location or one random user, there would be 13.8 users on the average in this uh, base stations, right? So a random user will see more load on its base station than the average load on the base station, right? And this result is generally used when you compute total number of uses the tag cell, or that will help us to compute what is the per user bandwidth or resource which is available, and that generally used to compute the rate coverage, right? This can also be used to compute what is the probability that the base station has no user, right? So when is that important? When you see that uh, there are suppose you want to switch off the base station which has no user, right, if there is no user in a cell, you can just switch off the base station. That will help us reduce power and interference problem, right? So if you want to compute the probability of inactivity, you can just compute from this distribution what is the probability that the number of users is 0, and this will help you to compute that inactivity parameter, inactivity probability.